You look up at the sky at night tonight, and some stars look a lot brighter than others. That is their apparent brightness. Okay, we don't know if they're actually brighter or just because maybe they're closer to us. That's why they appear brighter. Just like you could have a floodlight a mile away and a flashlight a foot away from you. The light from the flashlight might appear brighter because it's closer, when in fact the floodlight is really brighter, but it's farther away from you, so it doesn't look as bright. Apparent brightness is categorized from a range of 1 to 6. 1 is actually the brightest, and 6 is the dimmest. And this classification is actually expanded beyond this, so if it's a negative number, that means it's even brighter. Apparent magnitude is how bright it appears when we look at the sky at night. If we go 5 stages, we increase or decrease the magnitude by 100 times. The true magnitude of the stars are the true brightness of the star. So if the stars were the same distance from you, you compare the brightness there. The true brightness of the star is called the absolute magnitude of the star, the Alpha Centauri. But if you look up at the sky at night and look at their apparent magnitude, they're close. In fact, the Alpha Centauri is a little brighter. However, when we look at their absolute magnitude, how bright are they in reality, the Beta Centauri star is much, much, much brighter. The Alpha Centauri just looks brighter because it's closer to us. And that is why we use absolute magnitude when we want to really study and classify stars, because we want to figure out how bright are they in reality. What's their real brightness? What's the real magnitude of the stars? So now we know absolute magnitude of stars and apparent magnitude of stars. Another thing to classify stars we can use is color, because if you look at the stars at night, they're not all shining bright white. So the color of the stars is really a way of indicating their temperature. Remember, if we think about temperature, it's really the kinetic energy of the atoms. So how much they're moving, how fast they're moving around. And it's interesting, everything seems to be counterintuitive when studying stars. So the hotter the star is, the bluer the color. The cooler the star is, the redder the color is. So red is cool and blue is hot. And there's a range. Obviously the core of the star would be billions degrees Celsius. If we look at the stars, the color of the stars, we want to figure out, what does this tell us? What does this mean, the colors of these stars? And we use a scale of colors. The O is violet, blue, dark blue, A is lighter blue, F is really white, G is yellowish, K orange, and M red. So when we graph the classification of stars, this is another thing that's a little counterintuitive. On the x-axis, we will have this, but as you go this direction, the star temperature is getting cooler. Hotter stars are going to be those that look blue in the sky. The cooler stars are red color. Now, when we classify the stars, we can put them into a graph called the Hertzsprung-Russell diagram. Hertzsprung-Russell diagram. So these are two astronomers came together and showed how we can classify stars according to their magnitude, their absolute magnitude, which is how bright they are in reality, and their color, which is indication of the actual surface temperature of the stars. So let's classify some of these stars using the HR diagram. Now, when you set up this diagram, we have to have an x-axis and a y-axis. And another thing that's a little counterintuitive here is we have two of each. On the y-axis, the one on the left, we're actually going to put the absolute magnitude of the star. So how bright is it really? And again, remember that scale was ranged from 1 to 6, -6. Remember, so negatives are going to be very, very, very bright. positives, less bright. So the higher the number, the dimmer the stars are. We're going to have a range from 12, positive 12, to negative 6. So the stars up here are going to be the brightest. Down here are less bright, dimmer. The higher the number on the absolute magnitude scale, the dimmer the stars are. On the next y-axis, we're going to have luminosity, which is really the amount of energy that is released from the stars. And energy, in this case, is going to be really light energy. So luminosity So these numbers indicate the amount of energy produced from the stars in relationship to our sun. So at this level, if it's a 10, that means it has 10 times energy our sun produces. Stars here have 100 times the energy. 1,000, 10,000, and 100,000. Okay? This one would be a tenth of the energy produced. This one is a hundredth, and this one is a thousandth. This is a logarithmic scale. Instead of going up this scale by adding numbers, we actually go up by multiplying. So we are multiplying each of these as we go by 10. So for example, this one's 1, multiply 1 times 10, 10. Times 10, 100, times 10, 1,000, times 10, 10,000, times 10, 100,000. A star has an absolute magnitude of -6. Over here, it would be 100,000 times more energy produced than the energy produced from our suns. And down here, we're going to put the colors. Temperature, the color is indication of the temperature of the stars. The second x-axis is going to be the actual temperature. As we go this way, temperature gets cooler, which makes sense because we're going toward the red stars. As we go up, we are increasing the luminosity, which is the amount of energy produced from a star, relating it to the energy produced from the sun. And over here, absolute magnitude, or how bright the stars are. So as we go up, we're getting brighter stars and more energy. So the hottest, brightest stars are going to be in the upper left corner of the HR diagram, because we're looking at brightness. The more negative the number, the brighter the star. So we're up here. And temperature increases as you go from right to left. So hottest, brightest stars over here. Coolest, dimmest stars are going to be in the bottom right. Upper left, hot and bright. Down here, so if we were to graph stars using this diagram, it would look something like this. And 95% of the stars are actually close to this line. And this line represents 95% of the stars. So you can see how close, if I plotted the stars, this is what 95% would be along the line. So really that indicates as you get cooler, the temperature decreases, obviously. And it also is less bright. So the cooler stars, 95% of them are less bright, they're dimmer, less luminous, and they're cooler. And these stars, these 95% of the stars are called main sequence stars, because really they're on the main sequence, the main line here. The stars over here are dimmer and they're cooler. So they're not very bright and they're not very hot. So these stars over here are very hot and very bright, and they're very big, magnitude, large magnitude. So they burn up the fuel very fast. They're gas guzzlers. They burn up gas very fast. So when they're fast burning, that means the lifespan is shorter. So stars over here are not going to live as long. And technically they're not really alive, but we call it a lifespan or a life cycle of stars just because they're different phases the star goes through. So these are short-lived. Over here, these are longer lived. They're smaller stars, dimmer, and they're cooler, but they have a longer lifespan. There are more stars down here versus up here because these guzzle gas. They're gas guzzlers. They suck up all the fuel fast. They burn out fast. The lifespan is very short. Remember, 95% are main sequence, but we do have some here and here. So if we look at this, these are on the cooler end, so they're cooler. So these are red, but they're also brighter. Absolute magnitude is much greater, so they're bigger. And these are then red giants and red supergiants. The stars over here then, they're very hot, you can see, but the magnitude is lower and much less luminosity. So they're hot, very hot, but they're not very bright, be very small. So these are very small stars. These are very large. Stars over here are white dwarfs. Very, very small, but they're very, very hot.